Hi everyone. So, like I was mentioning earlier, this is not really going to be a talk in the sense of, there's this nice polished thing that I'm going to talk about. And so this is not something that, well, okay, the first half of it is going to be like a normal talk. The second half of it is not something that someone has done, and it's also not something that I have done. It's something that I'm in the process of doing. So, and I'm very much looking for input on that. But before we go there, so the first half of it. So last time, Miatek had this, I think, very interesting and very good talk on normalization by evaluation using Kripke semantics, right? I hope most of you attended that one, because I was trying to structure the first half in contrast to his approach. So okay, so basically, so what did he show, right? What he did was lifting the terms of our object language into the meta language, so turning things which have reduction rules into some representation in Agda which uses Agda's reduction rules to implement that reduction, right? And then pushing the results back into the object language. And it's a very nice technique, and it can be very mind-blowing, but maybe it's too mind-blowing. So because I'm thinking that, so if I look at that code, the semantics that it implements is not apparent, at least to me, right? So like, I can't remember if this came up at the meetup or maybe afterwards when I talked to Miatek, but I asked him like, what is the reduction strategy that it implements? And it's not easy to answer that question, because it depends on Agda's implementation strategy, it depends on how exactly you encode functions, etc. So what I want to show first is the dual of this, which is to just do symbolic manipulation, right? So what I mean by that is there's the pedestrian way of implementing a language, right? So let's look at this example. So I'm going to use, for the first half, a representation which is the same as what Miatek used, right? So we have types. So we have some base type, and we have a function type constructor, and then we have some context made up of types. I tried to use even the same constructor names to keep it consistent with Miatek's talk. And then we have variables which index into context, and then we have terms. So we have variables, lambda abstractions, and function application. So no changes here, right? So this is exactly the same as Miatek showed. But now, what do I mean by syntactic semantics, or implementing this in a syntactic way? Well, what I mean is simply saying that, okay, and this is a part where, is this still readable? No? Too small? See? Okay, no, because the lines are not getting really short. So here, right, I have an explicit reduction relation, right? So I have a relation which says that, for example, the first one, right, that if v is a value and I apply lambda f to v, then that can reduce to f by just pushing in the value, right? So this is taking a term on the object level, remaining on the object level. This is just manipulating symbols, right? I have a tree. Now, of course, behind this, and this is going to be important a bit later, behind this is a function that actually implements substitution. So I've hidden it here, but it's actually in one of these modules. So the idea is that there's an explicit representation of simultaneous substitution, simply as basically a mapping for each variable in scope. It will give you a term in some other, each variable in a context will give you some term in some other context, right? But if we have this, and we implement type preserving substitution, then we can write our semantics by saying, okay, so if I have this term, I do this manipulation, this transformation on it, and then I get a new term, right? So this, and similarly, if you have a function application, we can reduce the function side of it, and if the function side of it is already a value, then we can start reducing the argument, right? And what do we mean by value? Well, we just say what we want to consider as values. So here I say that lambda abstractions are the only values in this language, right? So what we have here, right, is none of this ever lifts up to the level of AGDA, right? Nothing gets turned in. Yes, question?
Sorry, I wasn't here last time.
Oh.
So this is it for.
Well, so in this case, it's okay. So it's either for interpretation or just proving things about languages. So in this case, because the example that I'm going to be using is showing strong normalization of simply typed lambda calculus, the same way that Mietek was showing. So in this case, the two are the same, right? Because a constructive proof that a language is strongly normalizing is an interpreter for it, right? So here it's an interpreter, but the same technique would apply to any other property of a language that you would want to talk about. So what I want to stress here is that everything just remains a term, right? So we have these syntactic things, and then we just have a relation between terms. So the left-hand side and the right-hand side of this stepping relation, they are still just terms. And when something becomes a value, for example, here when we say that we can only push in values, so whenever we apply a lambda on a value, we can substitute it in. That is done by having some extra constraint that a given term happens to be a value, or a representation of a value, if you will. But then we're still just but it's still just a term, right? So v is a term, and we have a proof that it's a value, but it's still just a term.
Sorry, the syntax of autoencode only works better?
Yes, yeah. So it's the same intrinsically typed representation that Mietek used. So everything above this line is exactly the same as last. Okay, sorry. So yeah, so this is a this is going to be important later on.
Term is a well-typed term of type tie in context gamma.
Exactly. That's exactly what it is. So yeah, and now if we have some reduction relation, we can of course take the transitive closure of it, transitive reflexive closure of it, and then we can define a concept of a normal form by any relation by saying that something is in normal form if it doesn't have, if there's no next step, right? And then we can say that a given term halts if it reduces to a value, right? Yes. So this is small step, and then we allow for many steps, and then we need to prove some properties about the semantics, because what we want to do here. So the goal with this is to prove something like this. So this says that any closed term E at any type halts, which we have defined as meaning it can be reduced in 0 or more steps into some other term which is a value, right? So this is what we want to prove. But how do we prove this, right? So in the normalization by evaluation approach, what we did was we lifted the terms into the meta level, and we gave a particular model of the terms such that we were able to push down the results of those terms into normal forms, right? But here we are not going to do any of that. Oh, and importantly, so the big idea in that one was in how do you choose the model, right? And that's where the Kripke model came into play. And of course, like, that's not something you can easily come up with. So that's where the smarts are done. Whereas here, I think so far we haven't done any smarts, but of course we haven't proven this yet either. So there is going to be a point where we do need to be smart. And so for this particular example, what I did was, well, first of all, there's a bunch of properties we can easily prove about our semantics, but on their own they might not look as useful. So one is that every value is in normal form, and then the other one is that our reduction relation is deterministic, and if we have a value then it halts. Okay, but why do we prove this? Well, it's because for this particular proof I used the STLC chapter of Software Foundations by Pierce and others. So they prove the strong normalization of STLC with a particular technique, and that technique is defining this property of a given term being saturated. And the crucial thing about this property is that if a term is saturated, then it halts, right? So now we can reduce the problem of showing that everything halts to a problem of showing that everything is saturated, right? But the definition of saturatedness and how we prove that, so this is where the smarts come in this technique. So I want to be clear on this, right? I'm not saying that in the purely syntactic route you will be able to do everything just mechanically by churning syntax. Non-trivial properties will need non-trivial proofs at some point. And in particular, here the non-triviality is in two parts, I think. So I would say that, starting with, okay, so if something halts and then we reduce it, then it will still halt. Okay, that's not a big thing. If something is saturated and then we reduce it, then it's still saturated. Okay, and it goes both ways, blah, blah, blah. But the meat of it comes here, where we can prove that any term is saturated, but not the term itself, but rather into any term we can substitute in a substitution which only contains values. So that's what an instantiation stands for. Maybe I should quickly scroll to the definition of it. So basically, a given substitution is an instantiation if it only contains closed terms. So every variable gets replaced by a closed term. And those are not just any terms, but they are values and saturated. So they're saturated values, if you want to say it in a more nice way. So, and again, this is not obvious, right? Like, what does this what does this whole notion of saturatedness have to do? No, we didn't have that. I mean, we would like that to hold because, well, but so how should I put it? That's something we can prove once we are done with everything. But here we can't use that yet. So it's easier to say that it's both. And then when we need to come up with a new instantiation, we will have a proof of saturatedness and a proof of valueness at hand, so we can make progress. So, so as I was saying, like, using this notion of saturated terms and using this notion of instantiation, because you would think that it's enough to just say that, okay, we're going to instantiate by values, but then there comes a point where you can't make an inductive step, basically. So again, so this is where one half of the smartness, or one half of the non-triviality comes from. And then the other part is what is hidden away at first sight. Because if you read everything that I have shown you so far, like, okay, so just to show you, so we only have a couple of lines left. So once we have proven that every term is saturated if we instantiate it, then at that point we're pretty much done, right? Because we will say that, okay, well, if we have a closed term, right, then we have an instantiation for the closed context trivially, because there are no variables, there's nothing to instantiate. So we just use the empty substitution and we saturate it, and what it gives us is a proof that this term with the empty instantiation pushed in is saturated, right? And then, like, because it's saturated, we know it halts. We've proven this before. But this gives us not a proof that E halts. It gives us a proof that E, with the empty substitution applied, halts. And this is the other part which is a bit tricky. So we need to be able to say that, oh, but if I substitute something with the trivial substitution, I get back the original thing. And also in this proof, there should be this lemma, which again says that if I substitute, okay, read from right left. So if I have some term f, and I substitute in some substitution sigma, but I shift it by one variable, meaning, if sigma assigns a given term to variable 0, I will assign it to variable 1. If it assigns a variable 1, I will assign it to variable 2, and so on. And then I substitute in the innermost single variable that remains as E prime, right, is the same as just putting the two substitutions next to each other and doing it simultaneously, right? So this is a trivial, like for a human, this is a trivial property, because that's what the simultaneity of simultaneous substitution means, right? But like, so this equation and this equation, we need to prove them. And this is kind of where we are getting to the meat of my second part, because, so originally I just wanted to talk about this, right? Originally I just wanted to show you that, okay, apart from the NB approach, there's also the more pedestrian, just churning terms approach. And I was working on, well, basically this. So I was working on transliterating the proof from the book, which is it. So the book shows everything in coq, and the book uses a untyped representation, and it uses names, like strings for names. So environments and contexts are a lot more messy because you can have autoscope references, and you have to prove that substitution is type preserving and all that. So I was working on translating that to Agda and using a type representation, and all the other stuff I was able to write because I had the book, right? I was cheating. I was following the proof from the book, and I was just rewriting Agda. But then, not this one, but this one turned out to be super complicated to prove, at least first, like before I knew what I was supposed to be doing. And I was banging my head against this for a long time. And then I talked to someone who knows about this stuff. So when I was back in Hungary, I was at a seminar, and I mentioned this problem to someone. And he was, so I told him, I'm working on this, and I have a particular lemma about substitution that I want to prove. And he was saying, okay, don't tell me what the proof what the theorem that you're trying to prove is. I don't care, because I can tell you that if you prove this, and there's like this long laundry list of properties about type preserving, simultaneous substitution, and renaming. And he was saying, okay, you prove all these, and I guarantee you will not see it first, right? It will look like a very boring long list of properties, but I guarantee you prove this, you will be able to prove this. And he was right. So the big hidden lie in all this, like the lie in all of this looking so simple, is because I have hidden this module here, the module which proves properties of substitution. Because what this does, right, is it proves things like composing substitutions, associativity of renaming versus substitution, and of course you can combine renamings and substitutions in many ways, so you get lots of these, right? You have reflexive, you have the fact that reflexive renaming can be combined with a substitution and then is the same as just the substitution. You can do it the other way around. So it's lots of these, right? Like you see, this is long and tedious stuff. And but this guy, András Kovács, who I was talking to, he didn't just tell me to go and implement this. He was also giving me a GitHub address where he has all these implemented. So I thought, oh, okay, well, I'm just going to import this. But if you look at that module, it starts with a comment saying, okay, this shows you everything you need to know about substitutions. And the way you use it is you copy-paste it into your own module, and then you customize it. Because so it's not a library, right? So because, of course it's not, because everything here is written in terms of my particular representation for terms. So for example, if I look at, let's look at an example. Okay, like this one, right? This is an easy one, but it says that if I substitute by the trivial substitution any term, I get back the original term. Well, how do you prove it? Well, it's easy because you just prove it by induction on the shape of the term, right? But these constructors, these come from my code. This is what we started with. Remember, I first said, okay, I'm going to use the same representation as MiaText, so I just put some code there, and these are the three constructors. But that means, this is in the middle of some proof about some boring property of substitution. So of course you can't librarize it this way. So, and this was the problem that I started thinking about because after I did all this, yes, of course he was right. I was able to write my proof. Like if I go back to, so what does that proof actually look like? Turns out it's not that complicated because this is the one, right? So it says that if I have some substitution sigma and I put in some extra variable and then I replace that variable with some term, is the same wait. Okay, so this is a slightly more general because it says basically that it doesn't matter what I put here, because if I do this first, it's gonna get rid of everything except the, it's like how should I put it? The only way the innermost variable will remain in the result of applying this is from some weakening. I mean, it can't appear, so it doesn't matter what I put here, because here I have already substituted everything away, and I just weakened the resulting term, so there can't be any actual variables in there. It's a term with one, which is not closed, it's open. It still has one variable in its context, but it's there because I weakened the closed term, right? And it's a two-liner. So it's trivial once you have the machinery, right? Once you have this kind of properties and this one, right? So what I think is a problem with a big problem with this approach is that what if I want to then change my language? So suppose that I want to add booleans, right? So I have here my type representation. So what would I need to change to add booleans? Well, the first thing I would need to do is, of course, is to add constructors for representing true and false as the constructors of bool, and to have a conditional expression constructor. So that's okay. So of course I have to do that because I'm defining a language, so I have to say what my language is. I have to say that, okay, now it has these extra terms. I don't have a problem with having to do this. Okay, I also have to extend my definition of what is a value because I want true and false to be values. Again, that's understandable. I'm the only one who knows what true and false should be. So, and I'm making a language. I need to be able to say what are the values. I also need to add new reduction rules, right? To basically to reduce the condition, and once it's true, I can reduce the whole conditional into the then branch, or if it's false, I can reduce it to the else branch. And again, it makes perfect sense that I have to do this. And then I have to extend my proofs of that every value is in normal form. I have to extend my proof that it's deterministic. But of course, I can't expect anyone to do this for me, because my particular reduction rules are my own, right? I could have added something different, and then I would need a different proof for this. However, if you actually look at the difference between the two files, okay, so what we have here, is this readable, or should I try increasing the font size? Yes, no, readable. Okay, so here you can see, okay, so I added bool to my type representing types. I added true, false, and conditionals. Okay, and then this is the first part that is not so nice. I also had to change my definition of applying a renaming on a term, because I have to do something with terms which are, booleans, right? And then similarly, I had to change my implementation of type preserving simultaneous substitution, because I have to be able to say, how do I substitute in a true, trivially, but I still have to write it. And then, okay, so this is, yes, they are the values and the reduction rules. Like I said, it's understandable. It's understandable to have to extend the proof of determinism. But if you scroll a bit further, you see these. We start seeing changes to the proofs of properties of renaming and substitution, right? So here, for example, it says, okay, I'm proving. So what is this? So it says that if I apply the trivial renaming on a term, I get back the original term, right? And to prove this, to keep this proof, I have to add cases for true and false and conditionals, right? Similarly, the other one is, I don't know, it's something about, it's something about how if you apply a renaming and then you apply another one, it's the same as applying the composition of the two renamings. Again, it's a property about renamings, but to prove it, you have to talk about the case where the term is true or false or conditional, right? And so on. So I'm going to scroll past the other ones, but you get the idea, right? So, and then finally we are back to our nice semantic world. So yeah, we have to change the proof that every term is saturated, but again, that's understandable because that's a property of the language. Like imagine if I added something to our language which would make it non-total, then I shouldn't be able to fill in this proof, but I still should be able to fill in all the proofs about substitution and renaming, right? So, and this concludes the first part, because the second part that I want to talk about is trying to solve this, trying to librarize these proofs so that you don't have to change any of them just because your language changes, right? So how do you do that? So I don't know, but I have an idea, which might be rubbish. So the idea is the following. The idea is the following. Instead of defining a data type which represents your terms of your language, instead the plan is that I give you a single data type, which I call code here, and it's a bit unfortunate that it doesn't all fit on one screen, but yeah, maybe like this. Okay, so the idea is that there's this type code. Okay, so this is something that a library gives you, like my library gives you. Right? And then you will describe your language as a value of this type. And we will see an example of what I mean by that. So the main prior work on this is that I found is this 2017 paper by McBride and McKenna and the other usual suspects of this field, scope-safe universe of syntaxes with binding. So that one is trying to solve this problem for untyped representation. So the idea there is you can express substitution and renaming if you know where new variables are bound, but there's no typing anywhere at all. So in their paper, they say, okay, so we're going to give you 3 ways of constructing a description of your language, right? So one will be to have a sigma-like thing. So this is how you put data into your nodes, or into your, how do you call these, like nodes, I guess, your grammar intermediate nodes. And then you have a constructor which says, okay, this is a child term, this is like a subterm with this many new variables in scope. Okay? And then you have the way of, like, you have to be able to end somehow, right? So it's like, so this is like think of it like a linked list, where at each step you either put some data there by using the sigma, or you put a placeholder for a subterm with a given number of new variables in scope in that subterm. Right? So for example, if you want to describe the simplified lambda calculus, you would write it as saying that lambda holds as data some type, right? Because when, like, suppose that you want to write it as lambda x colon t something, so it's not just lambda x something. Then the t would be stored in a sigma, and then in the body of the lambda abstraction, you have a new variable in scope, so this would be set to 1, right? And you can and you can recurse there, so you just put, I guess, done here, and then because you're done. I mean, that's the end of it, right? So it's one subterm with one new variable, and so that's what you put there. And for application, there's no data there, so it's like child 0, done, right? Because you have one subterm with no new terms, no new variables in scope, and another subterm also with no new variables in scope. So and together they form the application, like the left-hand side and the right-hand side. So my idea, and from here on, I would very much appreciate if you guys stop me anytime, either if you have a question or if you think there's something very wrong with this, okay? So my idea is change this so that we have a global view of all subterms, because here, right, if you have something like child 1, child 1, child 0, done, right?
The difference between child 0
No, child 0 means I have a subterm here. Like this term is made up of a subterm. Like
that's one unique subterm that doesn't bound anything.
But it's still but it's gonna be like, okay. Just because you have no new variables in scope doesn't mean that you have no way of expressing. Like, okay, think of something where there are no binders.
The term of your language into that desk thing, or you are putting the language itself.
The language itself. And then, okay, yes. So then there's a function which takes a description and gives you a type for a given description, which you can then use to represent terms or instances of your language. And the idea here is the same. But so to be able to do this typed, what I'm thinking of is that, okay, one problem with this one is that there's no point where you see all the types of all the subterms, because you don't see all the subterms. You only always see one subterm at a time, right? So instead of this, I'm saying, okay, what if, see? Oh, I thought it was the projector, thanks. Nice save. So instead of this, let me scroll down a bit. what if we only allow you to store data on the outside? So basically, you put your data as many as you want, but at some point you need to stop. And at that point, you need to use this node constructor, which instead of, I'm trying to look at my nodes, but I'm lost on them anyway. So instead of having a linked list of these, you say, okay, here's what I'm going to do. I will have this many new variables in scope for all the subterms. Okay? And then I will say for each of wait, something's not right here. Oh, yes, it is, yeah. So here, this is a number of new variables that are in scope. This shape, and I wish it fit on the screen, shape is a list of this many markers telling you, for every item in the list, it tells you which of these variables are visible in a given subterm. Okay, so the idea is that if you have something which has 3 subterms, this would be a list of 3 items, and each of the elements of the list is going to be a vector of this many elements, which tell you if that variable is in scope. So let me give you a quick example. Never mind that we haven't talked about typing yet, but just to give you an idea of the scoping, okay? So don't look at the second line yet, okay? So here, how do I encode a lambda? Well, in a lambda case, right, I have one new variable bound for the whole of the lambda, and I have one subterm. So this is why this list only has one element, right? And in that one subterm, I have to say which of my one variables are in scope. So I will say, okay, in this one child, the one new variable is bound, right? Which would mean exactly that in lambda abstraction, you have a subterm and you have a new variable in that subterm. It's like the trivial case that this is needlessly complicated for that. But it also allows us to express a let. The difference between the two is that in a let, you have 2 subterms, right? You have one new name, or one new variable. It's unbound in the first subterm because this is like let x equals this in this. So x is not in scope. X is not bound in the definition of x, but it's bound in the body of the let. Whereas if you want recursive lets, for let rec, we also introduce one new variable, but it's bound both in the definition of it and also in the body of it, right? So the difference between these two is that in a let, in the first subterm, the one new variable is not bound, whereas in the second one it is bound, right? Because syntactically, that's the only difference between let and let rec. We're not talking about semantics here, right? So the idea here is that you will define your semantics using symbolic, like reduction relation or NBE for all I care. But that's out of scope here. This is about, okay, but how do I even represent what my language is in a way that can be processed, right? And not just an opaque type, because then my opaque type and your opaque type will have nothing to do with each other, so we won't be able to librarize all these syntactic proofs. So, okay, so what about all those other lines? Because this, so far, what I explained, is just a different way of getting this well-scoped, scope-safe universe of syntaxes, right? But because we have a global view of all the possible, all the subterms in a given term, we can also add a well-typeness constraint. Okay, so the idea here is, you know how in Haskell, right, you have GADTs, but GADTs are compiled away into existentials and type equality constraints. Because, instead of, so in a GADT you have type indexes, right? Or indices. Whereas in a normal ADT, you only have type parameters. You have to be parametric in all your type arguments. But if you can add an equality constraint, it's forcing it, like, okay, how do I say it? So suppose that you want to write a constructor for a GADT where a given index is fixed to the unit type, right? That's the same as being parametric in some type and having a constraint that that type A is equal to unit, right? And that's exactly what happens inside. So system, what's it called, FC, doesn't have GADTs. It only has type equalities and existentials. And the idea here is the same, that instead of trying to get indices into your subterms, just make them parametric and then have an extra constraint. But this constraint is not necessarily a type equality. It can be whatever you want. Okay, so what is it? So it says it's going to be a proposition, right? Because it maps to set. And it's a proposition about n types. But those are going to be obviously the types of the n newly introduced variables, right? Then for every subterm, a type. So these are obviously the types of the subterms. And then it gets the type of the term we are producing. So this is where this trick of making it parametric by passing it here instead of having it as an index. So we pass it as a parameter, but then it's available here, so you can constrain it by having some proposition here which forces this to be of a given shape or a given value. So if we go back to the other example, like for a lambda, right, the proposition, the well-timeness constraint says that, okay, if the variable, the bound variable is of type t prime, and the body is of type u, and the whole lambda is of type t0, then t prime equals t. So again, t is of course what the user said, right? Because we said we have explicit types lambda. So so t prime is equal to t, and u, so the type of the body of the lambda abstraction is the type of the full thing is equal to function type from t to the body of the lambda abstraction. Right? So if I switch back for a second to the normal, the non-generic, let's call it the data type based representation, what we had here was that for a lambda abstraction, right? We have an index for the type of the term that we are representing, and here we set that index to t function from t to u, right? But if it's a parameter, we can't do this. It's some type that we are given. I think I called it t0, right? It's some t0 we have no control over, but we can say, okay, some t that we have no control over, but we say, but that t, this t0, oh, it's horrible, I wasn't using consistent names between the examples, sorry about that. So it's some t0, but we say that, okay, but we will need a witness that this t0 is equal to t to u, whereas in the other case we just match on the index being t to u. Okay, but that's the idea, because this means we can sidestep the question of how do you describe something that will get turned into an index data type in such a way that you can also represent it without the indices being available. Because one of the goals of this is, if you have this code, you should be able to get not just the typed representation, but also an untyped one, and also an unscoped one. Right? So, and I have that, so let me show you what I mean by that. So how do we do STLC using this? Well, it's basically we have all the pieces already because I've shown you what lambda looks like, and app is much simpler. So okay, we store some data, which is just a tag, because of course we want the sum type, right? Because a lambda term is either an application or a lambda abstraction. Of course, notably missing from here are variables, right? But of course, because we need to know, so variables, you get them for free if you use, when we turn a code into a type representation or any representation, it will have variables, because the whole point of this is to be able to describe languages which have variables, right? That's why we have a notion of binding and all that. So, so we match on the tag. If the tag is a lamb, well, this is the same type we saw before. And if it's an app, it's even simpler because we introduce 0 new variables, and we have 2 subterms, one where nothing is bound out of nothing, and another one where nothing is bound out of nothing. And then the typing constraint says that if the first subterm has type T1, and the second has type T2, and this has type T, then T1 needs to equal T2 to T. Right? So the type of the application, sorry, the type of the function is the type of the argument to the type of the application. So how do we then use this, right? So because this only describes our language, but it doesn't give us a way of representing terms. So the idea there is, if I can find it quickly. Okay, so the idea is, given a code, it will give you a type called term, which has, well, the same shape, right? So it has the context and it has the type. But this whole module is parameterized by a code. So this, for a given code, this will give you a given type. For different code, it will give you a different type. And to give you a feel of it, so I don't think we need to look at, unless there's some questions about the details of the type representation, but I think this gives you a good feel of it, that so these are pattern synonyms so that we can both match and construct terms, but you can think of them as just being smart constructors, right? So if you want to construct a lambda abstraction, so given a term of type u in an extended context, this will give us a term in the unextended context with the function type, right? It's the same. This is exactly the type of the lamb constructor of our original data type representation, but but it has this horrible looking definition. So this is using the constructors of the type representation that we have derived from this code. Right? Is this part clear? Like the relationship between the code and the and this type. Is this clear? Because the rest of it hinges on this. So here, right? When we put the witness of the typing constraint as using propositional equalities reflexivity, so this forces everything else to be of the right type, right? So unfortunately in Agda you can't put type signatures and pattern synonyms, so this is why this is only a comment. But this it really gets this type. So it will get the correct type of a lambda abstraction is a function type, because this witness of the pair of equalities forces it to be forces this type to be this, even though it's parametric. So one open question that I have about this is, what is the power of this approach of describing a type system with these local constraints? So I called the library simply typed because that seems to be a lower bound on the expressivity of it. Like I was able to do STLC on it, so yes, it can do a simplified language, but maybe it can do more. It's not obvious to me what exactly it can do, because you could be like here, this doesn't need to be an equality. This could be some subtyping relation. It could do some unification. If you have a decidable unification implementation, you could use it here, right? Now polymorphism is tricky, of course, because so far everything is only in one, everything only has one context. So I'm not, you would need two orthogonal contexts, I guess, to have a context of type variables. But maybe you don't. Maybe you can put some, maybe your type can instead be a sum type of either a type or a kind, and put type variables as just variables in the context.
For example, type class is an Haskell type or objects and access type of store.
Oh, you mean like if you have overloaded record fields turned on, or? But for normal type classes, you don't. So this. Hmm.
Because you have to basically alternate between the binding order you force here.
Okay, that's you mean because I have a separate untyped representation and I have
You have an untyped
but well scoped, yeah.
Representation.
Right. Oh, I see what you mean. But you don't have to use that. So if okay, I see what you mean. Okay, so the untyped and unscope checked representation that I give you works by allowing you to give this many names here, right? So if you have a lambda, you get one, you get one string. There's a placeholder for one string, or one whatever you want your names to be, and then that's what you refer to. But in what you're describing, I think you wouldn't be able to use that. But that's okay, because no one is forcing you to use the untyped, unscoped representation. So all the substitution lemmas are written in terms of the typed and scope check representation. So it's like everything is done. It's in a processed format. So it could be that you can't write your input language as the untyped representation, but yeah, but if you can jump, like if you can leapfrog the scope checker and jump straight to the typed one, then. But I don't know, because to be honest, that's something I haven't thought about at all. Like, what if your right? So this. But I mean, you can't even but if you want to be able to represent that in this type thing, right? You would either have a non-closed term, so you'd have all these in context, and you would need to point at the the resolved field names, etc. Or you would need to include your field definitions so that you can close the whole thing. Like I would imagine that in that language you would have something like a let data or. Ooh.
Because you can have a let with multiple elements. So either you whatever, but they want to bind 3 by time.
Okay. What you could do is put the number into a sigma, right? And then, given that number, you can just use that here. So you could have something which is like sigma net, and then lambda n 2 node n. Well, you would have to. I mean, yeah. So you would have to be able to programmatically. So it would be like some repeat of bound if you want all of them.
And once again, basically, but you can have a very complicated pattern to bindings at this level, but then your substitution.
No, but that's the thing. The substitution you really get for free. I'm going to show you that in a second. So substitution just works. So what the substitute.
Yeah, what you're doing when you write a term, basically, giving the tricky case of the substitution inside what it is.
Well, you're giving the structure of how bindings propagate. Yes. But yes, but yeah, exactly. But I mean, of course, there has to be a point where you describe how it propagates. But it will give you all the proofs that the substitution that it implements is not just a substitution; it's a substitution plus all the proofs. Yeah, all those properties, and those properties hold just because this code type tries to like circumscribe like it tries to carve out the valid syntaxes, right? So
Do you have a fixed property that?
What? Sorry.
Do you have a fixed property that you put on the substitution, or like on what you have? If I forgot one of the here forgot to state the preservation.
Yeah, but this doesn't say.
What do you get? I mean,
So this doesn't state the preservation of types as you do the substitution. You get that by construction of the substitution. So this is not about like this is not about this is not about preserving the type during substitution. That you can't escape. And that you get for free. I mean, depending on how you look at it, you get it for free or you can't escape.
find a code where you don't preserve type in substitution, basically.
No. No. So okay, let me put it this way. The substitution is the other way around. The substitution you get out of this will preserve types. But you can try.
If I describe a dummy language that does not preserve type, but the type do not. I don't know.
But wait, so
that rewrites an int to a string, and then when it breaks.
no, but wait. So okay. But in that language, that would be a reduction rule, not a substitution, right? I mean.
Well, you still have to.
Yes.
If I define an EO type language.
Oh, well, I mean, no, because the whole point of this is going to be this kind of yeah. So okay, so but yeah, it's not like I have too much to tell anymore. Okay, but yeah, point taken. So okay, we'll get back to this in a second. I don't want to bore David. So what does this give us, right? As you can imagine, the difference between the adding the bools is now restricted to just changing the code that we use and then changing the reduction rules, blah, blah, blah. But nowhere here will you see any change on the definition or the properties of substitutions. And of course, you can't see any change because it's not implemented here, right? Because there's a line here which imports the substitution stuff. And then there's a line later here which imports the properties of substitution. So of course, we can't change it just to add boost because the code is not even here. So it really is a proper library at this point. And then just as a quick example of what you can do with it. So here's also, okay, so, okay, let's show this one first. So this example is just a toy type checker for STLC. So all it does is given a scope checked expression with as many variables as the size of my context, right, will give me maybe it will give me a type that this can be type that. Now, of course, this is not, and it will give me such a type that if I erase the types, because So one of the things my library gives you is a generic type erasure function, that goes from the type representation to the scope representation. And this will give you a type term which erases to the original term. Now, of course, this is still not a total specification of a type checker, because this could always return nothing. So the real one would be a decider for well-typedness, not just a maybe typed thing. So it would need to give you a proof of either that it is well-typed. Well, it does that already, because it gives you a constructive proof by giving you the type term. Or it would need to give you a proof that it's untypable. And this one doesn't do this, but this is just a demo I threw together just to illustrate that. But you could write that. So there's nothing in, and if you look at the code, if you use these pattern synonyms, it's just as readable as it would be if we use the data type representation. And I think maybe this answers your question. So any intentional transformation or any intentional analysis you want to write, you're still able to, because you can recurse on to subterms, and you can pattern match on individual constructors. It's just that those constructors are, they don't look like this. They have that horrible shape, but you can abstract that away with the type synonyms, or the pattern synonyms. So, okay, I have another example for this. Somewhere. Okay, well, I look for it afterwards, but it's an example where I take a language where the tag itself is parameterized by whether it allows let or not. So you have an input language where you can have lets, and then your transformation which inlines all the lets and gives you an expression of, where the code is changed slightly so that the tag is proven not to be a let, right? Like we cut away one branch of, maybe I should try and find it just a sec. So it should, yeah. No, this does real inlining, just to, because the whole point of it is to demonstrate that it can be done, right? So I have a term, I have an input term, and I give you an inline term by just having a simultaneous substitution of inlined terms into variables of the input context, right? And it really is just what you would expect it to be, right? Oh, by the way, this reminds me, I wanted to mention this at some point. So one of McBride's paper on this topic introduces the beautiful concept of shiftable substitutions, which of course he calls substitution. I wanted to definitely include this. So this is not using substitutions. But does this answer your question? No. Okay. But the idea is that this is just an ad hoc. So the library is not going to give you this, of course. It doesn't know what it means to inline something, but you can write it yourself, staying in the generic representation. Yeah. Okay. But okay, we should talk afterwards. So I think that's basically it. Let me just quickly see what else I have. Yeah. Oh, okay. So this is like a big question. So about the typing constraints. So I'm not too familiar with bidirectional type systems, but it feels like maybe they could also help us out here. Like maybe explicitly marking which types or which constraints should flow upwards and which ones should be pushed down. But I don't know, because it's a bit of a unexplored world for me. But in case, like I was hoping maybe someone here has some experience with bidirectional type checkers. So anyway, so that's it. So again, I'm not saying that this necessarily has value. I'm just curious what we can come up with. I just think I'm onto something here, because it worked for the simplest possible example. So most of the job is done, right? But it seems to, like, if I try prodding it while still staying in a simply typed world, so far it seems to allow me to express all these languages. Yeah. So yeah, let's talk about this. That's basically my call to action with this talk. Yep, that's it.